In the earlier three parts of laws of motion, we have talked about the qualitative and quantitative definitions of force. We have further talked about various forces in nature and the force of friction. In the present concluding part 4, we will be talking about circular motion, the examples of circular motion and the centripetal force, the motion of a car on a level road, banking of curves, angle of banking required on a curved circular track with friction and without the use of friction. Let's now take some examples of circular motion. We have studied that circular motion, even if it is uniform, is an accelerated motion because it requires a continuous change in direction. For a body moving in a circular path of radius r with a uniform speed v, the acceleration called centripetal acceleration is given by the ratio v square over r. The acceleration, that is centripetal acceleration, acts along the radius and is directed towards the center of the circular path. According to second law, the required force, which we call centripetal force, denoted by Fc, is given by Fc is equal to mv square over r. The force is called centripetal force and is always essential to overcome the inertia of direction in a body. Now, some examples of centripetal force. The tension in the string provides the centripetal force for a stone rotated in a circle by a string. You must have tried this example. Whenever we move a stone along a circular path with the help of a string, a tension is produced in the string. The tension pulls the stone towards the center of the circular path, providing centripetal force. The gravitational force on a planet due to sun provides the centripetal force for motion of a planet around the sun. Likewise, the satellites are pulled towards the planets for their circular motion with gravitational force. The force of friction provides centripetal force for a car taking a circular turn on a horizontal road. Let's now take the specific example of a car taking a turn on a level road. Here in this diagram, you can see a car on a level road. R, capital R, denotes the radius of the circular path. The force required for circular motion is mv square over r. As you can see from the diagram, the forces acting on the car are the weight of the car mg vertically downwards, the normal reaction capital N vertically upwards, and the frictional force denoted by small f. As there is no acceleration in the vertical direction, we have n minus mg equal to 0. That is, there is equilibrium along the vertical direction, which gives us normal reaction equal to mg. The centripetal force required for circular motion along the surface of the road is provided by the friction between the car tires and the road. So, we can write F friction, that is Fr equal to F centripetal equal to mv square over r. It should be less than or equal to the maximum force of static friction, that is Fms. Or we can write mv square over r less than equal to mu s n, or mv square over r less than equal to mu s mg, because n is mg. This implies v square less than equal to mu s r g. Hence, for a given value of coefficient of static friction mu s and r, there is a maximum speed for the car to safely negotiate the curve. This speed is given by V maximum equal to mu s r g. The contribution of friction to the centripetal force, however, causes wear and tear of the tires of the car. Banking of curves. We have just now seen that on a level circular track, the force of friction between tires and the roads provides the necessary centripetal force for circular motion. This causes wear and tear of the tires, reducing the life of the tires. In order to reduce the wearing out of tires and to provide the necessary centripetal force, the roads are banked at the curves. That is, the outer edge of the road is raised with respect to the inner edge through a small angle theta, as is clear from the diagram. So, the outer edge is slightly higher than the inner edge of the road. This is called the banking of roads. This banking is essential on a circular track. It provides the necessary centripetal force. It enables the vehicles to negotiate the curves safely. If the centripetal force is not provided for, the vehicle would skid towards the outer edge and may overturn. The angle of banking depends on the radius of the curved path, the maximum safe speed of the vehicle on that road, the estimated friction between the tires and the road. A vehicle moving faster than the maximum safe speed for the given angle of banking and the coefficient of friction would skid off the road, causing accident. Now here we have a diagram of a car on a banked road. Here we will be calculating the angle of banking. We will totally eliminate the force of friction as provision for the centripetal force. The forces acting on the vehicle are its weight mg vertically downwards, normal reaction capital N perpendicular to the road surface. The vertical component N cos theta of the normal reaction balances the weight of the car, and the horizontal component provides the necessary centripetal force. So, we can write N sin theta equal to mv square over r and N cos theta equal to the weight mg. Equation 1 divided by 2 leads us to tangent theta equal to v square over rg. Hence, the maximum safe speed is given by v maximum equal to root rg tangent theta, and the angle of banking for a particular speed v will be given by theta equal to tangent inverse v square over rg. This gives us the angle of banking on a particular curved track for a maximum speed v. At velocities exceeding v maximum, friction also will have to contribute to the centripetal force, which we will discuss in the next part. Now we will discuss the motion of a car on a banked curved road with friction also contributing to the centripetal force. Have a close look at this diagram and carefully see the forces which are acting on the vehicle. The forces acting are its weight mg, the weight of the car vertically downward, the normal reaction capital N perpendicular to the road surface, the force of friction F parallel to the banked road and down the track, the normal reaction and the force of friction. They can be resolved along horizontal and vertical. The components of normal reaction are N cos theta vertically upward and N sin theta along horizontal. The components of the force of friction are F cos theta along horizontal and F sin theta vertically downward. The horizontal components provide the centripetal force for circular motion. Therefore, we have n sin theta plus f cos theta equal to mv square over r. As there is no acceleration along the vertical, we have n cos theta equal to mg plus f sin theta. Also, the maximum force of friction available is F max equal to mu s n. Using equation number 3 in 1 and 2, we get n sin theta plus mu s n cos theta equal to m v maximum square over r. So, n cos theta minus mu s n sin theta equal to mg is the condition for equilibrium in the vertical direction because there is no acceleration along vertical. Let us eliminate capital N, the normal reaction between the equations. We get V maximum equal to square root of gr into mu s plus tangent theta over 1 minus mu s tangent theta. This equation gives the maximum safe speed. In order to check the correctness of this equation, let us put mu s equal to 0. That is, we eliminate the role of the force of friction in centripetal force. This leads us to V maximum equal to Rg tangent theta, a relation which we derived earlier without contribution of the frictional force. Driving at speeds V exceeding V maximum is not safe, as the car is likely to skid towards the outer edge of the road and may overturn. Hence, the study of circular motion and the forces required help us design curved roads for safety. The study also sets the maximum safe speed limits under given circumstances to prevent accidents. Dear learners, physics is a science in which the concepts learnt are very useful in daily life. Let us now take a few examples to reinforce the concepts that we have learnt and see how they are useful in practical situations. Here, as an example, we have a cyclist speeding at 18 km per hour on a level road, taking a sharp circular turn of radius 3 meter without reducing the speed. The coefficient of static friction between the tires and the road is 0.1. Will the cyclist slip while taking the turn? Let us probe. In this example, we have to apply the concept we have learned for an unbanked circular track. On an unbanked road, the frictional force alone can provide the centripetal force required to keep the cyclist moving on a circular track without slipping. If the speed is too large, that is, it exceeds the maximum safe limit, the frictional force will not be sufficient to provide the necessary centripetal force and the cyclist will slip. Now, the condition for the cyclist not to slip is given by the equation v square, where v denotes the speed of the cyclist, should be less than mu s rg. Using the given values, that is radius equal to 3 meter, g equal to 9.8 meter per second square and mu s is equal to 0.1. That is, here one thing should be remembered, do not use g equal to 10 meter per second square for calculations, because 10 meter per second square being higher than 9.8 is only an approximate value and will give us a false higher value of the safe speed, which may cause accidents. So, using g equal to 9.8, we get v square is equal to 2.94 meter square per second square. For the cyclist, the speed is 18 kilometer per hour, which on conversion to SI units gives you 5 meter per second. Therefore, V square is 25 meter square per second square, far more than the maximum safe limit. So, as the speed of the cyclist exceeds the maximum safe limit, the cyclist will slip while taking this particular circular turn at 5 meter per second. Let us now take another example. A circular race track of radius 300 meter is banked at an angle of 15 degree. If the coefficient of friction between the wheels of the race car and the road is 0.2, then what is the optimum speed of the race car to avoid wear and tear of the tires, and the maximum permissible speed to avoid slipping using the friction also. Now, on this particular banked road, the horizontal component of the normal force and the horizontal component of the frictional force both will contribute to the centripetal force to keep the car moving on a circular turn without slipping. The component of normal reaction is enough to provide the needed centripetal force, and the frictional force is not needed in part 1. So, the optimum speed V is given by V maximum equal to square root of r g tangent theta. We are given radius of the track as 300 meter, angle of banking theta as 15 degree, g as we have stated earlier should be taken as 9.8 meter per second and not 10 meter per second square. Calculations give us V naught equal to root r g tangent theta equal to 28.1 meter per second. This value 28.1 meter per second is the maximum safe speed at which the car can negotiate the curve without using the force of friction. If the frictional force is also included, then the maximum permissible speed V maximum is given by the relation V maximum equal to square root of g into r mu s plus tangent theta over 1 minus mu s tangent theta, where mu s is the coefficient of static friction. Using the known values of the various symbols in the formula, we get the maximum safe speed including the force of friction for centripetal force as 38.1 meter per second. So, for this particular track, if the speed of the car exceeds 38.1, it will be unsafe. Below 38.1 meter per second, the racing car can safely negotiate the curve. Now, let us learn a few points which we have to keep in mind while solving numerical problems in mechanics. In order to solve the problems in mechanics systematically, one should use the following steps. Number 1, draw a diagram showing various parts of the assembly of the bodies, their links. Links we mean they may be interconnected by strings, they may be interconnected by springs, they may be on the supports, etc. Choose any convenient part of the assembly as one system. That is, if you want to find acceleration of a particular object, say a block in the system, concentrate on that particular block. Draw a separate diagram which shows this particular part of the system, that is the block alone. Mark all the forces on the system by remaining parts of the assembly. You must include the forces on the system by other agencies. The weight of the body or block, the tension in the strings or springs which are given in the problem, and the frictional force should also be considered and shown in the diagram. Do not include the forces by this block on the other objects. This is important because we have to study motion of the block, and hence forces acting on the block and not by the block should be included. The diagram of this type, which shows the block and the forces, is known as free body diagram of the block or the part of the system. In a free body diagram, we include information about the magnitude as well as the direction of the forces. Identify the unknowns to be determined using the laws of motion. Apply the laws of motion, the principle of conservation of momentum, etc., to find the unknown quantities. Repeat for other parts of the system as required, that is, you may draw free body diagram for other blocks or other objects if you are asked to calculate the acceleration or forces on the other block. Dear learners, in the ongoing 4-part series of videos on laws of motion, we have been able to discuss the basic fundamental concepts in the unit. The concepts discussed herein will help you understand the unit. The videos, however, do not comprehensively cover the syllabus. The learners should reinforce the concepts learned through problem solving. Please refer to NCERT textbook for completeness of the syllabus. Thank you.